Thank you for this introduction, and it's a pleasure to be here in this wonderful city. In this talk, I'd like to discuss what the universe looks like very far away from here, in regions so remote that they cannot be observed directly. There is a limit to how far we can see into the universe, and this is set by the distance that light has traveled since the Big Bang, about 14 billion light years. More remote objects cannot be seen, simply suppose their light has not yet reached us. And the question is, what lies beyond this cosmic horizon? Until relatively recently, cosmologists believed that the answer to this question is very simple. It is just more of the same, more galaxies and more stars. But recent developments in cosmology and in particle physics have led to a drastic revision of this view. And the new worldview that has emerged says that these remote regions are strikingly different from what we see around here, and may even be described by different laws of physics. This new picture is based on the theory of cosmic inflation, and I'm going to tell you what this theory is and why we should believe it. And to set the stage for this discussion, let me first very briefly review the standard Big Bang cosmology, which was the prevailing theory before inflation was introduced. So this is a very brief summary of the Big Bang cosmology. It says that the universe as we know it began in a big explosion, which we call the Big Bang. Here time goes from bottom up. This explosion occurred not at some particular place in the universe, but everywhere at once. And at that time the universe was filled with extremely hot and dense and rapidly expanding fireball of elementary particles and radiation. As it expanded, this fireball cooled down, and in about a couple of minutes it was cool enough for atomic nuclei to form. And then it took about 1 million years for these nuclei to combine with electrons to form neutral atoms. And at that point, the universe became transparent to light. So we can now see light, radiation, coming to us from this primeval fireball. And this radiation comes to us from all directions in the sky. This is what is called cosmic background radiation. Another important feature of this primeval fireball is that it was extremely uniform. But there were very tiny non-uniformities. Some regions were slightly more dense than others. And then these overdense regions, in the course of billions of years, they attracted matter from surrounding regions and became even more dense, and eventually they evolved into galaxies. And this took about 10 billion years. And finally, we appeared on the scene in a very recent cosmic past. There is a wealth of observational data that supports this theory, so there is very little doubt that it is basically correct. For one thing, we see distant galaxies moving away from us at very high speeds, and this indicates that the universe is expanding. Also, this theory explains very accurately the amount of light elements like helium and lithium observed in the universe. These elements were formed in this primeval nucleosynthesis in a few minutes after the Big Bang. But the most important evidence, you could say the smoking gun of the Big Bang, is the cosmic background radiation. The Bang happened 14 billion years ago, but the radiation is still there for us to explore, and 2 Nobel Prizes were already awarded for the study of this cosmic background radiation. So obviously we have a very successful theory. However, it leaves some very intriguing questions without answers. Questions about what actually happened at this mysterious moment of the Big Bang. Why was the universe so hot? Why was it expanding? Why was it so uniform or homogeneous? And then what is the origin of these small inhomogeneities that later evolved into galaxies? And finally, what happened before the Big Bang? All of these questions are addressed in the theory of cosmic inflation. This theory was proposed by Alan Guth about 30 years ago, with some key insight contributed by Andrei Linde. So here they are. This is Alan in his office in at MIT. I should tell you that Alan won the prize for the messiest office in the Boston area. It's not a joke. It was a real contest which was conducted by our newspaper, Boston Globe, and many people were nominated. Alan won the contest, and you can see that his office is indeed very messy. This picture makes me feel better about my own office. So let me now tell you about the theory of inflation that these two fellows have developed. The key role in this theory is played by a peculiar form of matter which is called false vacuum. Vacuum is what you get when you remove all particles and radiation. So this is basically empty space. So I tried to depict it in this view graph. It looks like nothing, but for a physicist, a vacuum is very different from nothing. It is a physical object which is endowed with energy and pressure, and the properties of elementary particles are determined by the properties of the vacuum. So the vacuum can be in different energy states, and properties of elementary particles change as you go from one state to the other. We live in a very low energy vacuum, and for a long time it was believed that our vacuum has exactly zero energy, but now we have strong evidence that in fact the energy of our vacuum is very small but non-zero. Modern theories of elementary particles tell us that in addition to our vacuum, there exist a number of high energy vacua, which are called false vacua. And these are the objects that play a role in cosmic inflation. So let me tell you a little about the properties of these false vacua. So first of all, a false vacuum has a high energy density. So each cubic centimeter of space carries a tremendous energy. And by Einstein's energy-mass relation, it also has a very large mass, which suggests that it produces a strong gravitational field. Also, false vacuum has large negative pressure. Positive pressure is the force pushing outward, like you have in a tire in a car. Negative pressure is what you have in a stretched piece of rubber, so it is the force pushing inward. And false vacuum has this kind of pressure, tension, it is called. Now, the most peculiar property of the false vacuum is its gravity. In Einstein's theory of relativity, gravitational field is produced not only by energy or mass, but also by pressure. And positive pressure produces an attractive gravitational force, and negative pressure produces a repulsive force. And the negative pressure of the false vacuum is so large that this repulsive force overcomes the attractive force due to energy, and the overall effect is gravitational repulsion. So the false vacuum is gravitationally repulsive, and this is the key property that plays the role in cosmic inflation. And finally, this kind of vacuum is unstable. It has very high energy density, and it decays, typically in a very short time, into our low energy vacuum. And this excess energy goes to produce a hot fireball of particles. So this is all we need to know about false vacuum. And now we are ready to discuss the theory of inflation. So what Alan Guth suggested is that the early universe, somewhere at very early times, was in the state of false vacuum. Now, why is that? This is a good question, and I'll have something to say about it at the end of the talk. But now let us assume with Alan Guth that this was actually so, that initially the universe is filled with false vacuum. Then the repulsive gravity of this false vacuum causes the universe to expand with acceleration. And if you solve Einstein's equations, you discover that this sort of expansion has the property that the size of the universe doubles every given interval of time. So there is certain doubling time after which the universe doubles. This is like similar to actually what happens in economic inflation. If you have constant inflation rate, then the prices would double every, say, 10 years. Cosmic inflation is a lot faster than that. Here this doubling time is a tiny fraction of a second. And so the resulting expansion is so fast that starting from a very small, say, subatomic region of space, the universe is blown up to dimensions much bigger than what we can currently observe. And eventually, so this tremendously fast kind of explosive expansion happens, and then eventually, because false vacuum is unstable, it decays, producing this fireball of particles, and that's when inflation ends, and the following evolution follows the line of the standard cosmology. So now you have a fireball, and it expands by inertia. Now, this model explains very nicely the features of the Big Bang, which seemed so mysterious before. The high temperature is explained by the high energy of the false vacuum, right? Because all this energy went to produce this hot fireball. The expansion is due to the repulsive gravity. It causes the universe to expand, and then the fireball expands by inertia. Homogeneity also is explained because false vacuum is very homogeneous. It has the same energy density everywhere. And small inhomogeneities took a little more effort to explain, and this was done by these two people in Russia. And I will not get into details of that. These inhomogeneities are explained by quantum fluctuations during inflation, and the predictions of this theory agree very well with observations. So, as Alan Guth says, what previously was called the theory of the Big Bang was actually the theory of the aftermath of the bang, aftermath of the explosion. It didn't say much about what happened at the explosion itself, and now inflation is the theory of the bang, of the Big Bang, of actually what happened during this short interval of time prior to creation of the fireball. So when Alan Guth suggested his theory, it was just a speculative hypothesis, but now there is very impressive evidence for inflation. Most of it comes from the cosmic microwave background and was obtained by this satellite, WMAP, Wilkinson Microwave Anisotropy Probe, which produced a map of the cosmic background radiation on the sky. So these different colors correspond to different intensity of the radiation. The radiation actually is very uniform, and these differences in color correspond to differences about 1 in 100,000. So it is a very accurate measurement. And then it was kind of, this map was processed mathematically, resulting in these dots. These are data points. And this red curve is a theoretical curve. So you see that agreement between the theory and observation is rather spectacular. Another prediction of inflation is that the universe should be flat on the largest scales. Einstein's theory allows the universe to be curved, the space to be curved. But according to inflation, nevertheless, on the largest scales it should be flat. And this is easy to understand. If you imagine a curved surface like a sphere, for example, and then you imagine enlarging it by a huge factor. This is what happens to the universe during inflation. Then we can see only a small part of this universe. And the small part of the sphere looks like a plane, so the universe looks flat. And that was confirmed by observations. Okay, so now we have reasons to believe that inflation indeed happened in our part of the universe. And then we can believe, at least have some trust in what the theory tells us about what the universe looks like beyond the observable region. And this brings me to what I started with. What does the universe look like on the largest scales, beyond what we can see? And what theory tells us is somewhat surprising. It tells us that although inflation ended in our part of the universe, it's still continuous in remote regions. And the end of inflation, that plays the role of the Big Bang in this theory, is not a unique event in the history of the universe. Other bangs happened in distant regions before that, and countless Big Bangs will occur afterwards. So this, in this sense, inflation is eternal. So you have this eternally inflating universe, and here and there you have these Big Bangs happening, producing fireballs and galaxies and stars. If you could see this universe, inflating universe from outside, this is what it would look like. So this yellow background is false vacuum. Now you can imagine it expanding very fast in all directions. And then decay of false vacuum occurs like boiling of water. So these bubbles of low energy vacuum state pop out here and there, and then they expand. Normally, if you have expanding bubbles, they would collide. But here, this false vacuum between them is expanding even faster. So these bubbles are driven apart. They very rarely collide, only when they form very close to one another. And once they are driven apart, this makes room for new bubbles to form. And this process continues forever. Now, we live in one of these bubbles, and we can see only a small part of it. We cannot travel to other bubbles. Even if we get into a spaceship and move as fast as we cannot catch up with the expanding boundaries of our bubble. So for all practical purposes, each bubble is a separate bubble universe. And an unlimited number of such bubble universes is formed in the course of eternal inflation. Now, if we cannot travel to other bubbles, how can we test this theory? In physics, of course, it's important for any hypothesis, it's important to indicate a way in which it can be tested or falsified. A very interesting way to test the theory is to look for bubble collisions. Although they're rare, they do occur, and in fact, since each bubble is expanding forever, it will collide with an infinite number of other bubbles, because the probability is non-zero, and it happens an infinite number of times in infinite time. If such a collision happens, we can look for signatures of these collisions in the cosmic microwave background. And this search is now underway. Some candidate kind of spots in the microwave background have been found, but there is no convincing evidence yet. But this would be very exciting, of course, if we had a direct test of eternal inflation by finding a signature that stands well above the background. I should say, though, that there is no guarantee that such a collision with another bubble occurred within our observable region. If it didn't, then we will have to look for indirect tests of eternal inflation. And I'll talk about this a bit later, but first let me well, I would say somewhat disturbing implication of this picture of the universe. It's remarkable, but somewhat disturbing, at least in my view. So, since we have this eternal inflation, in the course of eternal inflation, an infinite number of regions like ours, like the entire observable region, 14 billion light years, an infinite number of such regions will be formed. And these regions will start with somewhat different initial state, because the initial states in each region are determined by quantum fluctuations during inflation. So all possible initial states will be realized, and therefore all possible states of these regions will occur in all possible states that have non-zero probability. Now, an important point is that the number of possible states is finite, This may seem surprising because, for example, if I take this pointer and I move it by a meter, then I can move it by half a meter, can move it by a quarter a meter, and it seems that I already have an infinity of possible configurations right there, where this displacement is decreased by a factor of 2. However, when the displacement gets very small, such states cannot be distinguished in principle because of quantum mechanical uncertainty. So, because of quantum mechanics, the number of states in any finite region of space is finite. For a region of the size of our horizon, this number has been estimated as 10 to the 10 to the 120, which is an unimaginably large number, but the important point is that it is not an infinite number, it's a finite number of states. Now we have an infinite number of regions and a finite number of states that can occur in these regions. The inevitable conclusion is that each possible state is repeated an infinite number of times. So there will be an infinite number of regions identical to ours. In particular, there is an infinite number of Earths which are indistinguishable from ours, and I have to say there is an infinite number of your duplicates listening to this same talk. So I find this somewhat depressing, but if the theory of inflation is accepted, this conclusion is hard to avoid. Okay, so let us move on. Now, so far, I assumed that these different bubbles have the same physical properties. This does not have to be so. The physical properties of our world are determined by a set of numbers which are called constants of nature. And these are numbers like the masses of elementary particles, like Newton's gravitational constant, charges of particles, and so forth. Altogether, there are about 30 numbers. And if you write these numbers on a piece of paper, some of them are large, some of them are small. It seems that there is no system behind these numbers. For a long time, it has been a dream of particle physicists that someday all these numbers will be derived from some fundamental theory of nature. But there has been very little progress in that direction. On the other hand, some people notice that there does seem to be a system in these numbers, but not of the kind that particle physicists have been hoping for. These numbers seem to be fine-tuned for our existence. So let me just give you one example of what it means, this fine-tuning. Let me take the neutron mass. Atomic nuclei consists of neutrons and protons, and neutron is slightly heavier than the proton. It has no electric charge, while proton is positively charged. And outside the nucleus, neutron decays into proton and lighter particles. But inside the nucleus, it is stabilized by nuclear forces. So this is basically all we need to know about neutrons. And it is the positive charge of the protons that keeps electrons bound in atoms. And that's why we have chemistry. Okay, now imagine that we decrease the mass of the neutron by 1%. What would happen? If we do that, neutron would become lighter than the proton. And then protons would decay into neutrons and lighter particles. As a result, the nucleus will lose its electric charge, and electrons will fly away. So we will not have any chemistry in such a universe in which the neutron is only 1% lighter. If you increase the mass of the neutron by 1%, then it becomes so unstable that it decays even inside the nucleus. So the neutrons will decay into protons and lighter particles which fly away. And so the nucleus now consists only of protons. And then the electric repulsion between these protons will tear the nucleus apart. And so the protons will fly away. And the only atom that can exist in such a universe is one proton with one electron. So this is hydrogen. So if we change the neutron mass by 1%, one way or the other, we end up either in a universe without atoms or in a universe where only hydrogen can exist. And it's hard to imagine that life can exist in any universe like that. So it seems that, and the situation is about the same with other constants of nature. If you change them by relatively small amounts, you end up in a universe which is not biofriendly, which is not hospitable to life. So it seems that the constants of nature were fine-tuned by the Creator to have a universe where we can exist. There is, however, another possibility, which maybe gives a different image of the Creator. If He creates a huge number of universes at random, with random values of the constants, and then, purely by accident, in some of these universes, the constants happen to have values for which life can exist. And in those rare universes, intelligent creatures will evolve and will marvel at this fine-tuning of the constants. And this is exactly the possibility suggested by particle physics. In particular, string theory, which our best candidate now for the fundamental theory of nature, predicts the existence of huge number of different vacuum states with different values of constants of nature. Estimates go as high as 10 to the 500. And if you combine these ideas with eternal inflation, then bubbles of all kinds, all these 10 to the 500 kinds of types of bubbles, will be formed. And this would be the picture of bubbles within bubbles within bubbles. So these inflating false vacuum produces these yellow bubbles, and yellow bubbles, in turn, there is some inflation inside, and they produce these different colors correspond to different types of vacua having different values of the constants. So this is what is called the multiverse. And most of these bubbles will have no observers there, they will be barren. But only rare bubbles like ours will have inhabitants, but in these barren bubbles there is of course nobody there to complain about that. So this picture of the multiverse explains the fine-tuning in this way, that the number of possibilities is so huge that by pure accident there are some bubbles in which are biofriendly. This is sometimes called the anthropic principle, that we can only exist in those bubbles which are suitable for life. This, of course, is a statement which is obviously true. It's a somewhat trivial statement. But it can be turned into a testable prediction if we change it a little bit. Instead of anthropic principle, we can adopt what I call the principle of mediocrity. And this is to say that, okay, there are some observers living in different kinds of bubbles, And let us assume that we are typical among those observers. Okay, we can ask what a typical observer, that is the observer whose numbers who are more numerous than other kinds of observers. If we figure out what a typical observer will observe, what values of the constants of nature such an observer will measure, we can then make a prediction that this is what we expect to measure. That involves the assumption that we are unexceptional in the multiverse, that we are typical. But this is an assumption that has been very fruitful in cosmology, and so it makes sense to adopt it. This strategy has been applied to the energy density of our vacuum, which is also called the dark energy or the cosmological constant. And in fact, the prediction was successful, although very few people believed in it at the time when it was made. So this may be our first evidence that indeed there exists this huge multiverse out there. Okay, so I would like to spend the remaining few minutes to discuss this question about the beginning of the universe. I described the picture of the universe which expands without bound and with this eternal inflation and new big bangs occurring all the time. So this universe doesn't have an end. And a natural question to ask here is it possible that it also has no beginning? Many people find this possibility very attractive because beginning, of course, has many perplexing problems associated with it. In particular, what caused the beginning of the universe? What sets the initial conditions at the beginning of the universe? So this universe without a beginning was an attractive possibility, but there is an unexpected obstacle towards constructing such a picture. And this is a theorem that I proved with Arvind Borde and Alan Guth, which says that even though inflation is eternal to the future, it cannot be eternal to the past. This figure illustrates the proof of the theorem, in which I won't get into it, but actually the proof is rather elementary. And I should say that there are other theorems about the necessity of beginning of the universe. Initially, this whole field was initiated by Penrose and Hawking, but those theorems made pretty strong assumptions. They made assumptions about the content of the universe, what kind of matter fills the universe, and also about its global properties. What's interesting about this theorem that we proved here is that it is purely kinematic theorem. It doesn't assume anything about what kind of material fills the universe. It doesn't assume anything about even the nature of equations that describe the universe. Could be Einstein's equations can be modified. What it does assume is that the universe is expanding. So it follows that inflation must have a beginning, because inflation obviously is an expanding stage in the universe. And if inflation has a beginning, then a natural question is what happened before inflation. And before I even try to answer this question, you can tell me that I'm not going to give you a satisfactory answer, because you can keep asking, and what happened before that? So it appears that the most fundamental question of cosmology, of what was the beginning of the universe, does not really have a satisfactory answer. In fact, there is one scenario in which this infinite regress problem can be addressed, and this is the idea of creation of the universe from nothing. Now, normally we say that nothing can be created out of nothing, and for a physicist, the basis for this statement is basically the conservation laws. Energy is conserved, and energy of matter is positive. So whatever came before the universe has to have the same energy. However, it is a mathematical fact that the energy of a closed universe is exactly equal to zero. So the space of the universe can close on itself, just like the surface of the sphere. So in such a universe, if I go, say, in one direction and keep going, I'll come back from there. So it's just like if I go on a sphere in the same direction, I come back to the same point. So in such a closed universe, if I have a closed universe, the energy of matter is positive, but the energy of gravity is negative. And you can prove that for a closed universe, these two things exactly cancel one another. Another conserved quantity is electric charge. And for a closed universe, again, the electric charge must be equal to zero. And this, again, is not difficult to understand. If you imagine a sphere, again, to a low-dimensional analogy, and you put a positive charge on the north pole of the sphere, so there are lines of force coming out, lines of electric field coming out of this charge. And if you follow these lines, they will meet at the south pole. And that means that at the south pole, you must have a negative charge of equal magnitude. So you cannot put a charge in a closed universe without, at the same time, putting an opposite charge. The total charge must be zero. So if all conserved quantities of a closed universe are equal to zero, then nothing prevents such a universe from being spontaneously created out of nothing. And in fact, in quantum mechanics, anything that is not specifically forbidden by conservation laws happens with some probability. So we should conclude that closed universes should pop out of nothing, and like bubbles in a glass of champagne. There will be bubbles of different size, so these closed universes can have different size, different initial radius, and they can be filled with different kind of vacuum. There is an elegant mathematical description of this process, and you find that the most likely initial state of the universe is the closed universe of the smallest size, filled with the highest energy false vacuum. And this provides the initial state for inflation. So this is the beginning, provides the beginning for the story of eternal inflation. So this universe pops out, filled with very high energy vacuum. It immediately starts inflating, and then eternal inflation takes over. The difference between universes popping out of nothing and bubbles in a glass of champagne is that in champagne, bubbles form in liquid. And in the case of universe popping out of nothing, there is literally nothing outside. So the entire space is the space, the closed space that is being created. And in general relativity, space and time form a unit entity, space-time. So time also begins when the universe just formed. So the time starts ticking when the universe pops out of nothing. A similar picture was suggested by St. Augustine many centuries ago. He was struggling with the question of what God was doing before he created heaven and earth. And he concluded in the end, well, this is described in his wonderful book, Confessions, his struggle with his question. And he concluded that, in fact, time was created with the universe, and so it is meaningless to ask what God was doing before. And a very similar answer is given by modern cosmology. Now, when I say universe is created out of nothing, I put nothing in quotation marks. And the reason is that this process of creation of the universe, the quantum appearance of the universe, is described by the same mathematical equations that describe the following evolution of the universe. So what this suggests is somehow even before the creation of the universe, the laws of nature were already there, because the process of creation is described by the same laws. What does it mean for these laws of nature to have this Platonic existence? We cannot really tell. And also why the laws of nature have this particular form that they have, we also have no idea. So this brings us very far into the unknown, and this is probably a good place to stop. So thank you.